Control Systems, Lecture 6, Rotational System Transfer Functions. In this lecture, we will explore rotational transfer system functions, drawing on parallels to the translational mechanical systems we looked at in the previous lecture. Key concepts covered include understanding the rotational mechanical components, which are torque, inertia, and angular displacement, deriving the equations of motions for rotational systems, analyzing torsional stiffness and rotational damping, constructing free body diagrams for rotating masses, and finally computing transfer functions for rotational systems. So here's a typical system we'll look at. We have a rod that's supported by two bearings. So here, these are going to be handled similar to what we did for the mechanical systems, except that in this case, torque replaces force and angular displacement replaces translational displacements. And also the components undergo a rotation instead of a translation. So just like with translational systems, we can have a spring, a damper, and a mass, except here we're going to look at rotation. We'll apply a torque and look at an angular change. And so we can, on the right-hand column, we can find the impedance. So for spring, again, it transfers as K. For damper, it's the damper times S. And for the rotational mass, it's J times S squared. So you can see this is very similar to the translational case. So let's take a look at example 219. We want to find the transfer function theta 2 over Ts for the rotational system shown in figure A. So here we have a rod that's supported by bearings at each end. It's undergoing torsion. The torque is applied to the left, and the displacement is measured on the right. So we can take our system and we want to break it into a more detailed diagram. So we're going to approximate the system by assuming that the torsion acts like a spring concentrated at one particular point on the rod with inertia 1 and inertia 2. We also assume that the damping inside the flexible shaft is negligible. So here we're going to imagine that, for simplification purposes, that our system is modeled as on the right. So we have a damper, two inertia masses, a spring in between the masses, and a damper at each end. Notice here the torque is applied on the left. So you have an angular displacement on this mass and an angular displacement on this mass. So like before, let's take a look at J1. So here, in the case of J1, we have torques. Figure A here shows that the torques on J1 due only to the motion of J1. So what that's going to be, you have the torque applied here. It's going to turn, and if the torque is applied clockwise, the motion on theta 1 is going to be the clockwise. So that's the mass J1 times S squared is going to be opposed to that. You'll also have a damper times S1, the theta 1, that's opposed to that. And you have K times theta 1S, that also. So these motions are going to oppose the torque. Now let's look at the torques on J1 simply due to J2. So in other words, if I hold this J1 steady and I turn J2, this spring is going to turn, which in fact is going to turn J1. So here, if I turn this guy, this mass is going to cause this one to turn, so we'll have K times theta 2 felt on J1. So you can put both of these together, and you can come up with a kind of a combined diagram in part C. And we can do exactly the same thing for J2. If we look at the torques on J2, only the motion of J2 by itself, again, we can write equivalent terms. If we look at, keeping J2 steady and turning this one by itself, well, then again, it's felt through the spring. So we have a motion as such. And then we can put these two masses, these two diagrams together in part C. This is the final three-body diagram. So here from the first set of equations for J1, we can write our two equations of motion. So we have J1s squared plus D1s plus K times theta 1 minus K times theta 2 equals T sub S, because the torque is only acting on J1. Now from this diagram, we can write, notice here that minus K theta 2 gets replaced by minus K theta 1. This is very similar to the mechanical and electrical systems we showed before, where this term gets repeated, except that we replace the theta 2 by the theta 1. Plus, we have to add J2S squared plus D2S plus K times theta 2. In this case, this equals 0 because the torque doesn't act on J2. So here we have two equations again with two unknowns. We can solve this using Kramer's rule, or we can write an array, a set of matrices and use MATLAB to solve. So if we want to find the transfer function G sub S, which is theta 2 over the torque, here I'll show you how to do it in MATLAB. I define symbolic constants, theta S, J1, D1, K, T, J2, D2, theta 1, and theta 2. A and B are simply the matrices that I showed in the previous slide. C is the right-hand side. B is we find B, which is the solving for the variables, and so theta 2 here is going to be B sub 2. So here the G sub S is theta 2 over torque, and so here I simply write out, this is the transfer function here. And you can see how much simpler it is to do in MATLAB, but solving this by hand is not pretty, and it could take a while. So again, on your exams, you can use MATLAB to solve these. So finally, the transfer function, as showed in the previous slide for MATLAB, is given by the following equation. So our book gives you a skill assessment to do. They want you to solve the following system. It shows you the answer for the transfer function. And you can log into the Wiley website and check your solution. All right, I'll see you in the next lecture.